Okay, last time we started with general two impulse transfer as part of trajectory transfer. So, we continue with that. So, we took the case where we had the inner orbit whose radius is given by r I and the final orbit whose radius is r f, and a satellite is moving in the inner radius orbit and it has to be transferred into the outer radius orbit, but not along the tangential path. Means we are not starting here in this point and then starting tangentially here in this point and going up to this point. Rather, at intermediate point anywhere we are passing from point A to point B. Okay. So, this is not Hohmann transfer what we have been discussing. So, for this kind of treatment we need to generalize further how to find out the delta V required here in this place and the delta V required here in this place. So, for that VIC here is given, the which is the speed in the velocity in the circular orbit, and similarly for the velocity in the outer orbit is also known to us, which is VFC. So, this is the velocity in the outer orbit. So, if VIE is the velocity in the elliptical orbit in which the satellite is to be put for the transfer purpose, and from there then again it will be thrown into the, it will be put into the final this in the final circular orbit. So, for sending it along this direction, so we need a velocity which is given by VIE. Now, VIE is the velocity, required velocity. So, how much change in velocity is given, how much change in velocity is required, that is given by delta VI. So, we have started working with this. So, we have the velocity in the inner circular orbit which is given by mu by r I. Okay. VIE is the velocity in the elliptic orbit at point A we will consider, and again at point B also we will consider. So, we can put here subscript later on, but VIE indicates the velocity in the elliptic orbit, and we can put a subscript here to indicate that this is at point A. Okay. And VFE is the velocity in the elliptic orbit at B. Okay. So, VF, and here we have put the final to indicate this is corresponding to this point, otherwise the same thing could have been indicated by we can take it like the V eccentric V elliptical A and V elliptical B we can write, but here we have written V f, means this is the initial point here, starting point in the initial orbit, and this is the point in the final orbit. So, corresponding to that this subscript I and f they are appearing, okay. And E is corresponding to the elliptical orbit, and finally, we can put a subscript here B to indicate that this is at point B. So, that completes our notation, and the VFC, this is the velocity in the final circular orbit. C stands for the circular orbit, which is given by mu by r f, velocity in the circular orbit at B. Okay. So, after completing this, we assumed the quantities like V cap is equal to V by VIC, where VIC is the velocity in the initial circular orbit. So, this implies VI cap, VIC cap, this will be given by VIC divided by VIC equal to 1, and similarly VFC will be VFC by VIC. So, this is 1 by root n. Now, therefore, delta Vi this can be calculated. So, how much this delta Vi is, that can be calculated from here. Delta Vi is equal to VIE minus VIC. So, this is the velocity in the elliptic orbit at A and velocity in the circular orbit at A, okay. And this quantity in the scalar notation can be written like this. Okay. Similarly, we have written last time that delta Vf is equal to Vfc, which is the velocity in the final circular orbit minus Vfe. So, for that we have the case here, this is the velocity in the circular orbit, we put here v f c, and this is the velocity in the elliptical orbit, which is shown by here the blue color arrow. So, this is v f e, and these are at point B. So, we can put a subscript here B. So, we can insert a subscript here B to indicate that this is the velocity in the circular and the elliptic orbit at B. Okay. Therefore, delta V f, this will be given by this particular equation. So, we worked out till this extent last time. So, now we start working further. So, what we have got, delta V I square, this is equal to V I square plus V I c square minus 2 V I e times V I c to cos alpha I. This is equation 1, and the equation 2 is delta V f square, this is equal to so, here the notation A and B, they are not appearing. So, if we want, we can put here as A, and here we can put as B, okay, but it is a convenient to drop this subscript, because if we connote this I with the initial and F with the final. So, automatically this will give you the meaningful expression. So, so further while carrying out the work. So, we are going to drop this subscript A and subscript V. Now, we know that V in an elliptical orbit, it is given by mu times 2 by r minus 1 by a under root. So, here A is the semi major axis of the ellipse, so therefore, we will have now V I e. So, we are dropping the subscript A. So, V I e can be written as V I e mu square is equal to mu times 2 by r I minus 1 by a. Now, a we can express as, or rather say L we can write as, which is the semi lattice rectum this is equal to a times 1 minus e square. So, we can put here, insert here in this place two by r I, and a will be L by 1 minus e square. R I we can take it outside, and we can express it like this. So, mu by r I is nothing but V I c, which is the velocity in the circular orbit square. So, this becomes minus 2 times 2 minus 1 minus e square, and L by r I we write as L cap. So, where L by r I, this is equal to L cap. So, we have got a very simple expression for V I e written in terms of V I c. So, going further into it is, now V I e divided by V I c, this can be written as V I e cap. okay, according to our notation that we have developed earlier. So, this becomes V I E cap square, this will be equal to this. From here we can find it out. So, just we have to divide both sides by V I C square. So, we get this quantity here. So, this is our expression number 3. Similarly, at point B in the outer orbit, we can write V F E square, this is equal to mu times 2 by R F minus 1 by E, where A is the semi major axis of the transfer orbit, which is the elliptical orbit. Okay. So, therefore, this is 2 by R F minus 1 minus E square by L. Okay. And we can take it out, R I we can take as the common. So, this can be then expressed as 2 R I divided by R F minus okay. Now, we have the known quantities here. So, mu by R I is nothing but V I C square, and this we can write as 2 R F by R I minus 1 minus C square L by R I. Okay. So, this is V I C square times 2 by R F by R I is nothing but N. Okay. From the beginning we have been assuming this quantity. So, this is 2 divided by N and L by R I is nothing but L cap. So, thus what we get here V F E square divided by V I C square, this is equal to 2 by N minus 1 minus C square L cap. Okay. So, from here we can write following the earlier notation. So, V F E by V I C, this is nothing but V F E cap. Okay. This is the notation that will follow, and therefore, V F E square V F E cap square, this becomes equal to 2 by N minus 1 minus C square by L cap. So, this is our equation number 4. Okay. Now, going back into our old figures. So, here if we look into this figure, so what are the quantities to be found further is this alpha I, which is the angle from here to here, this is the angle alpha I, and the angle between this and this is alpha f. Okay. So, these two need to be worked out. So, now say this is our transfer trajectory. This is v theta, Okay, and here we can show this as V r. So, this is the velocity vector V. So, we will do a new figure for this. This figure is little blurred. B theta is perpendicular to the radius vector. This is the radius vector here. And suppose the velocity will be tangential to the trajectory. So, velocity can be shown along this direction as v, and this is v theta. So, if you look into this, the flight path angle is defined as the angle between the local horizontal. So, in the case of the this trajectory transfer or the any particle moving in a gravity field. So, this particular angle we can write here as alpha, and this is called the flight path angle. So, alpha is flight path and V r will be just in the radial direction. So, if this is the direction of r, okay, so here we will have V r in this direction. So, we have V theta here, V here and V r along this direction. So, resultant of these two will be the velocity vector V. So, what we have done here, so this is the velocity vector and which is V, and this is our V theta and this is our V r. So, where V is the resultant of V r and V theta, and the angle from here to here, this we have shown as angle alpha, which is the flight path angle. So, taking the same in the perspective of say around the earth, this is the earth and in some orbit, here we are showing this as the circular orbit, but suppose this is little bit elliptical. Okay. So, we have this angle as theta, we are measuring the true anomaly from this place, and then V theta will be perpendicular to this radius vector r. So, V theta will be along this direction, and suppose this is elliptical, then V direction will be tangent to the path. So, let us make it little bit elliptical, okay, so that we can show here V and this is now V r. So, this depicts the real picture in the case of our maybe any heavenly body. In this case, we are taking this as the earth, and around that in a circular in an elliptical orbit or in any trajectory, some particle is moving under gravity. So, this is the real situation which is shown here. So, this is our V vector and this is the resultant vector. So, V theta and V r. So, we are taking it in a proper way. V theta and this is V r. Okay. And the flight path angle, obviously, we have told that in that case this will be indicated by the angle from here to here, which is nothing but alpha. So, whatever we have shown here, this is a generalized representation. So, with this representation, what we want to work out, what will be the value of tan alpha, and then if we find out tan alpha. So, from here we will be able to find out the value of cos alpha. Okay. So, this is a generalized representation, and the representation that we follow here, this is for our the gravitational case. So, this angle obviously we have written as alpha. So, we can write tan alpha, this is equal to V r by V theta, and V r is nothing but r dot, and V theta is nothing but r times theta dot, and therefore, this becomes dr by dt into d theta. We can write it in this way. So, this becomes 1 by r into dr by d theta. So, now given tan alpha is equal to 1 by r dr by d theta, we can utilize the relationship for the ellipse developed earlier, which is L by r equal to 1 plus e cos theta, to work out the value of tan alpha. So, from here we can find out the value of dr by d theta. So, differentiating this gives us L by r square times dr by d theta So, thus we will have L by or either we can because what we need is 1 by r times dr by d theta. So, we put on the left hand side 1 by r times dr by d theta, and L and r we can take on the right hand side. So, we will have r times e sin theta divided by L. Okay. So, this implies tan alpha I, this will be nothing but 1 by r I times dr by d theta equal to r I times c sin theta divided by L. And we will put a subscript I to indicate the true anomaly at the initial point, so theta I, and L divided by r I, this will become L cap. So, thus tan alpha I is equal to E sin theta I divided by L cap. This is our equation number 5. Okay. Similarly, we can work out for the tan alpha f. So, again we will have for tan alpha f equal to 1 by r f times dr by d theta and this will be nothing but r f times E sin theta f divided by L. So, this we can express as r f by r I and L by r I, and r f by r I is nothing but n, and L by r I is nothing but L cap. So, this is E sin theta f. So, thus tan alpha f, this becomes equal to n by L cap This is our equation number 6. Okay, once we have got this, so from here now it is easy to work out. Now, the quantity which is present here, which is theta f and theta I, these two also need to be eliminated. Now, theta I and theta f in equations five and 6 need to be eliminated. Okay, and this we can do using the original equation which is given to us, which is L by R is equal to 1 by E cos theta. So, from here we can replace theta in terms of L and R and E. So, this implies now L by R I. So, if we take here as theta I, so we will have L by R I is equal to 1 plus E cos theta I. So, this implies L cap equal to 1 plus E cos theta I, and from here we get L cap minus 1 cos theta I, and this implies so this is our sin theta I. Similarly, we will have L by R f is equal to 1 by E cos theta f. So, this implies L by R I divided by R f R I plus E cos theta f, and this implies L cap by N is equal to 1 plus E cos theta f, and this implies cos theta f equal to L cap divided by N minus 1 times 1 by and therefore, sin theta f then becomes 1 minus 1 by E square times L cap N divided by N minus 1 whole square under root. This is our equation number 8. Okay, once we have got this, now we can write tan alpha I equal to E sin theta I by L cap. So, this will be E by L cap, and sin theta I is our 1 minus L cap minus 1 whole square divided by A square under root. So, taking E inside, So, this implies cos alpha A equal to and if you do the processing. So, you can prove that this quantity will be equal to, by inserting this quantity here in this place, this will turn out to be 1 by L cap divided by E square plus 2 L cap minus 1 under root. Okay. Similarly, you have tan alpha f equal to n by L cap E sin theta f, and the sin theta f just now we have worked out. So, the sin theta value is given here. So, we can insert here in this place, this way L cap times C sin theta f 1 minus 1 by E square. Okay. And if you simplify it, so from here we can find out cos alpha f. Okay, inserting these values and simplifying it, finally you will get L cap divided by 2 Okay, so, we have got finally the alpha I and alpha f. So, our job is done, and therefore, delta V I, this can be written as V I E square plus V I C square minus 2 V I E times 2 V I C Okay, so this is the equation that we wrote. So, these are the two equations. So, insert the value of the cos alpha I and cos alpha f in these two equation 1 and 2. So, after inserting the value, okay, so these are the two equations which are available to us, and these two will give us the amount of impulse required, but we need to further simplify these two equations. So, the notations that we have developed earlier, that if we divide the whole thing by V I C in this equation. Okay, so, delta V I square, this can be written as delta V I by V I C square, and V I C divided by V I C, this will become 1. So, this particular thing will write here as 1 and plus V I E by V I C square minus and here VIC cancels out and we get VIE by VIC times L cap by E square plus 2 L cap minus 1 under root. So, this implies delta V I cap square equal to. So, do the simplification by putting the values of VIE and VI by VIE by VIC. So, this will be 1 plus VIE by VIC. Earlier we have derived this quantity is nothing but 2 minus 1 minus E square L cap. So, 2 times this is 2 times VIE by VIC is 2 times 2 minus 1 minus E square by L cap, and this multiplied by L cap divided by E square plus 2 L cap minus 1 under root. Okay. And then simplifying, this will give you 3 minus 1 minus E square this is our equation number 10. Similarly, delta Vf is our Vfe square plus Vfc square minus 2 cos alpha f, okay, dividing both sides by Vic. Vfe divided by Vic square cos alpha f. So, therefore, we can write as delta Vf cap square. Okay. Here we have taken the under root. So, we remove the square term here. Okay, this is fine. So, delta Vf by Vic, this will be nothing but delta Vf cap. So, delta Vf cap square, then this becomes. Now, we need to insert these values here Vfc by Vic and Vfe by Vic, and all these quantities we have developed earlier. So, Vfc by Vic is nothing but 1 by n under root, and Vfe by Vic, this is nothing but 2 divided by n minus by L cap, and then minus 2 times this is one quantity, another quantity we have 1 by n under root, and times cos alpha I, which is nothing but L cap divided by 2 L cap n plus C square minus 1. So, if we do the simplification, what we get delta Vf cap equal to 3 by n minus 1 by a square divided by L cap minus 2 by n times L cap divided by n under root. And this is our equation number 11. So, these two equations give you the impulses in terms of delta V I cap and V f cap at the point A and B. So, delta V I cap is at the point A and delta V f cap this is at the point B, and this quantity is nothing but if you multiply this quantity by delta V, this multiply this by V I c. So, this gives you the actual amount of impulse. So, this equation looks very elegant and this is simple to work with, and therefore, this representation has been taken up. Okay. So, this is the generalized transfer, and the generalized transfer just now we have worked, this is and the earlier the particular transfer for the what we have termed as the Hohmann transfer we have taken, okay, in which we transferred from point A to point B in an elliptical orbit. This is minimum eccentric elliptical orbit, and we proved this also in the beginning of the trajectory transfer lectures. So, this is the whatever we have worked out, the which is representing the generalized transfer. Okay. So, from here this you can reduce to this particular case, because in this particular case alpha I and alpha f both will be equal to 0. Okay. So, for Hohmann transfer, alpha I equal to 0 and alpha f equal to 0. So, if we take these two, so it is easy to work out, and what ultimately you get the same result. So, those results we can show as so, what you need to do for that, we had the equation where delta V I by V I c square we wrote as 1 plus V I e by V I c square minus 2 V I e by V I c and V I c by V I c, okay, times cos alpha I. So, the cos alpha I, once alpha I equal to 0. So, the cos alpha I becomes equal to 1, and therefore, what you get the remaining quantity which is present here. So, this can be written as 1 minus V I e by this quantity becomes equal to 1. So, this becomes V I by V I c. We will write this as V I e by V I c minus 1 square. Okay, so, this implies V I delta V I by V I c why we have written in this format, because V I is greater than V I c, okay, and therefore, it is appropriate to represent it like this. Okay. Similarly, you can work out for delta V f by V I c, and if you try to equate, then you will see that the results are same for both this case and this case, there is no difference. Okay, so, this you can take up as a exercise, and we can go to the next topic. Okay. So, once we have done this, now the obviously while starting in the beginning we discussed that Hohmann transfer is the minimum eccentricity transfer, okay. But how efficient this is, that was not solved. So, that we can solve further by taking what is called the bielliptic case. So, bielliptic case, in that case we have one circular orbit like this and another circular orbit like this. Okay. So, instead of transferring from point A to point B here, the transfer starts like at point A, the impulse is given and it is the satellite goes into an elliptical orbit which is shown like this. Okay. So, this is point A and the point B is shown here in this point, and again at B an impulse is given. So, that satellite comes and becomes tangential at this point. So, at that point then we give an impulse of delta V c in the negative direction of course. So, this is the point C and that will put it into the circular orbit. So, here the impulse required is delta V a and here the impulse required is delta V b, and here a negative impulse is given to put it in this circular orbit, and this is the center. So, this is called bielliptic So, Hohmann transfer, this is not always cheaper. So, as the radius inner and the outer radius difference increases. So, say this is the inner radius r I here, okay, and r f tends to infinity. So, we keep it increasing the outer radius, and then we want to take it the satellite from point A to point C in the outer circle, then which one will be more effective, okay, Hohmann transfer or bielliptic transfer. So, the question here can be posed as given two orbits of radius r I and r f, where r f is greater than r I, then find out either Hohmann transfer will be more efficient or bielliptic transfer will be more efficient. So, before we go into the bielliptic transfer, we need to work further on the how much energy is required in the Hohmann transfer as we increase the radius of the circle r f, and this we have done earlier also. So, if you remember in our lecture number 3, in the lecture number 23. So, this was the we started from this point at point A and we give the impulse delta V I, okay, and finally, at point B we give the impulse delta V f, and these were the results obtained. Okay. So, we can utilize this result So, for Hohmann transfer, so we can write here as delta V A, this is equal to V I C times 2 n by n plus 1 under root minus 1, and delta V B equal to V F C times 1 minus 2 by n plus 1 under root. Okay, starting with these two equations, Therefore, delta V A plus delta V B. So, V I C we can write as mu by R I under root and similarly V F C we can write mu by R F under root times 1 minus 2 by n plus 1 under root. Okay. So, if we take mu R I outside, means we are virtually taking V I C outside. So, if we take V I C as the common, so what we get here 2 n by n plus 1 under root minus 1 into V F C by V I C. Okay. Now, V F C by V I C can be written in terms of R F and R I. So, we have V F C by V I C, this is nothing but mu by R F C under root divided by mu by R I C under root. So, thus we have delta V equal to delta V A plus delta V B is equal to V I C times 2 n divided by n plus 1 under root minus 1 plus and V F C by V I C, this we can show as write as here 1 by n under root. And close the bracket. Okay, so, this implies delta V by V I C So, in this representation some simplification can be done. If you try to write it further, simplify it. So, this can be written as 1 minus 1 by n times 2 n by 1 plus n under root. So, whatever we get here in this place, n is a quantity which we have written as R f by R I. So, if n tends to infinity, that is R f becomes very large with respect to R I. So, once n becomes very large, so this particular quantity can be written as delta V by V I C, this then becomes 1 minus 0 and this 2, here n we can divide it by n. So, this will become 2 divided by 1 plus 0 plus 1 by large quantity n is equal to infinity. So, this becomes the next term 0 and minus 1. So, what we get here, this is under root 2 minus 1. So, this is the limiting case. So, if you remember in the earlier we have written that in the parabolic orbit velocity is will be given as root 2 times v circular orbit, okay, and therefore, the difference in the velocity in the parabolic orbit and the circular orbit V p minus V c, this becomes root 2 minus 1 times V c. Okay, this is parabolic orbit. Okay. So, in this case what is happening, we have been working with the elliptical orbit, but as the value of R f increases, okay, R f goes up. So, similarly E goes up. Okay. So, for the elliptical orbit, so finally, once R f becomes infinite, so E will be equal to 1 at that time, and once E equal to 1. So, this is referring nothing but to the parabolic orbit, for which the difference in the velocity is given here by this equation, and this equation both are same, there is no difference. So, in the limiting case elliptical orbit also this acts as the parabolic orbit. So, we will continue with this, and we will try to find out what will be the efficiency of the Hohmann orbit, the Hohmann transfer and the bielliptic transfer, and we will try to do some comparison for that in the next lecture. Thank you very much.